Yeah. Mm-hmm. Okay.
It's like thing that you mount on the wall, right?
Mm-hmm.
To something in it, or you can put a handle,
Yeah.
something that holds something.
Yeah. Mm-hmm.
Okay, just to clarify.
Yeah.
Thank you.
Yeah. Mm-hmm. Hey Maxwell, how's it going? Yeah.
So activity four, the same model. I'm doing it on the same thing because my first computer has 2024
Yeah.
too. So the like screenshots I'm gonna put on are pictures from my phone. Is that okay?
Yeah.
Okay.
That's
I just
fine.
want to make sure you're looking like, is he grabbing like another student?
Oh, no. Yeah. I mean, the activities I mostly just great for completion.
Okay.
I mean, I'll see if you're really doing it on a different
No,
project.
that's what is like, so you do like, there are pictures of like the screen, they're not gonna be like screenshots.
Yeah. That's fine. I mean, for the midterm project, it should be nice. Screenshots.
No, yeah,
For the
that's fine.
activity, I don't.
Okay, just wanna make sure.
Yeah. Mhm. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, we're at the end of week 8, so this is technically the midpoint of the semester after today. Although we have 1 week for Thanksgiving, and so that week doesn't count. But technically, the 16-week semester, this is kind of the midpoint. Yeah, so we're halfway to Christmas, so that's a good thing. All right, so the plan for today, so I just have a regular lecture for you guys today. We're going to finish up our lecture notes on the direct stiffness method. So we have a little bit more to talk about in terms of the boundary conditions. So we kind of left it there a little bit. And then I have kind of one kind of longer example to kind of do with you guys. Okay. And so through that example, hopefully you'll kind of get a sense of kind of what the direct stiffness method entails and kind of all the steps to the problems that we're going to be doing. Okay. So the next few weeks are going to be, I will kind of be the first to admit that the next few weeks are going to be pretty repetitive. So we're going to be doing all stiffness type problems. So the exact process that you're going to go through is the same for every single problem. It's just that there's slight variations in terms of the types of elements that we'll see. So get used to this process. We're going to be doing it a lot. You're going to be seeing a lot of matrices, a lot of big matrices, a lot of kind of filling in stuff. So it gets a little bit repetitive. So I try not to linger here as much as I can, but To a certain degree, I can't really help it. That's just kind of how the material is. Okay. All right, so one announcement I want to make. So activity 4, remember, is due tomorrow, and your midterm project is due in about 2 weeks. And so if you haven't started on your midterm project, after you kind of get activity 4 in, that would be a good time to start. So I don't plan on assigning you guys anything until the midterm project is due. So the next 2 weeks is going to be dedicated to just kind of midterm project. So if you haven't started yet, if you have questions, come to office hours, send me emails, and so get your questions answered early, because right before it's due on Halloween and everything, that's when I get kind of a big rush of questions. And so, I try to answer the questions as quickly as I can at that point. But, when 20, 30 people are asking me things, it's a little bit hard to keep up with. So, start early, get your questions in early so that you can kind of finish early. So it's not as stressful. Okay. All right. Any questions I can answer before we get started today? All right, okay, so let's go ahead and get started. So we're gonna pick up where we left off on Tuesday. Okay. Okay, I was just making sure the microphone was good. Okay, so actually I'm gonna scroll up here a little bit. Okay. So last time, we were working on this example here. All right, so we had a 2-spring system. Their behavior is governed by their spring constants Ka and Kb. We are pulling on the second spring with a tensile force F, and we wanted to solve for the equilibrium positions of our 3 nodes here, D1, D2, and D3. Okay. And so we kind of started the direct stiffness process, where we started with the element stiffness matrices of each of the individual springs. And so we wrote out the element stiffness matrix for element A, the element stiffness matrix for element B, and then we assembled them together into one big 3x3 matrix. Okay. So that's kind of what we did here. So here you can see we have a 3x3 matrix. We have 1 row and 1 column for every degree of freedom that we have, D1, D2, D3. Okay. And we filled in the spots of this matrix according to our, 2 element stiffness matrices. Okay. All right, and so the last thing that we did here was that we needed to modify this matrix according to our boundary conditions. Okay, because what we said was that this matrix by itself we can't actually solve it yet because the matrix is symmetric. Our right-hand side vector right now is kind of undefined, and so we need to apply boundary conditions in order to make everything good. Okay. Okay. So we started our discussion on that, right? And so remember, we kind of reminded ourselves that there are 2 types of boundary conditions. There are constraint type boundary conditions, things like your fixed supports and ANSYS, and we have our load type boundary conditions. And so those are things like pressures and forces that we can apply in ANSYS. And the way we treat those 2 types of boundary conditions mathematically are going to be different, okay? So we started talking about the load type boundary condition first. And so the load type boundary condition, a lot of times this is going to be some kind of force that we're going to apply at a node. Okay. And so to apply a load type boundary condition to our direct stiffness method, we basically just plug it straight into our right-hand side forcing vector. Okay. And so we kind of illustrated that up here, where if we go back to our original problem, we can see here that on node 3, we're applying a tensile force F on node 3, right? And so what that tells us is that, F3, okay, the force on node 3 is going to be a capital F, okay? And so if we go back to our global stiffness system, okay, we can see here that we apply that boundary condition by replacing little f3 in our right-hand side forcing vector with big F, okay? All right, so load type boundary conditions are pretty straightforward. So basically we just take whatever value of the force and we just plug it into the appropriate spot on the right-hand side forcing vector, okay? Okay, so that's where we left off. So, that was a little bit fast, but, that was all just kind of a recap from Tuesday. Any questions on kind of the process up to this point? Okay, all right, so let's go ahead and keep going. Okay, so the next type boundary condition that we're going to apply is a constraint type boundary condition. Okay. All right, so just to kind of remind you, a constraint type boundary condition, the way that they work is that they directly specify the values of our primary variables. Okay. So when we first kind of defined these, a few weeks ago when we were talking about boundary conditions, we kind of did so in kind of a kind of in a hand wavy kind of way, right? So I mentioned that for every type of finite element simulation, there's always a primary variable which you solve for first. Okay. Now, hopefully that we're kind of doing this direct stiffness method, you'll kind of get a better understanding of what it means to be a primary variable. Okay. So for structures, okay. So for structural simulations, the primary variable that we're solving for first is the deformation for the displacement. Okay. And so any boundary condition that directly sets the value of the displacement or the deformation at a node is going to be a constraint type boundary condition. Okay. Okay. So let me kind of draw out our problem here again one more time. Okay. So I'm going to focus on our three nodes here. So we have one node that is attached to the wall, a second node that's in between the two springs, and the third node that's on the right. Okay. And each of these nodes, we're computing how much they are going to deform from their original positions. So D1, D2, D3, these represent the displacement of those locations in the system from their original, where they originally started. Okay. So any boundary condition that's directly specifies or directly constrains the values of either D1, D2, or D3 is going to be a constraint type boundary condition. Okay. All right, so let's look at all the conditions of all three nodes here, and let's determine whether they are being constrained or not. Okay. Okay, so let's start with D1. Okay, we're just going to go right to or left to right, excuse me. Okay, so node 1 here is attached directly to a fixed wall. Okay. So in other words, node 1 here is being anchored to something that's relatively fixed. Okay. So that tells us here that the value of D1 here is probably going to be fixed. It's going to be fixed at 0. Or I should say node 1 is not going to move. Node 1 is not going to move from that spot because it's fixed to the wall. Okay. So that's a pretty good indication that we're going to have a constraint type boundary condition applied at node 1. Okay. Okay. Let's look at node 2. Use orange. Okay, node 2 here is in between our two springs, right? So there's nothing really fixing it down because how much node 2 is going to deform is going to depend on how the two springs, how they're going to deform as well, okay? So node 2 here is not constrained by anything. And then same thing for node 3. So node 3 is being acted on by a force, right? So I didn't draw it here, but there's a tensile force being applied on node 3. Okay. So node 3 actually already has a boundary condition being applied. And so it has a load type boundary condition. So node 3 here, just by definition of having a load type boundary condition applied to it, is also not going to be constrained. Okay. All right, so we only have one node here that's going to have its value constrained, and that is node 1. Okay. Okay. And so taking that information, the fact that node 1 is not going to move from that spot, right? Mathematically, we can express that with a very simple equation that D1 is equal to 0. Okay. All that explanation, just kind of a very simple for you. Okay. All right. So that's good. So that's our constraint equation. Okay. Now this equation is eventually going to have to make its way into our our matrix system. Okay. Because remember the way that we defined our matrix system was a 3x3 system of equations, right? So 3 equations that we're going to solve for are 3 unknowns, D1, D2, and D3. Okay. Okay. So our matrix system already has 3 equations that we have for our 3 unknowns. Okay. But we have this constraint equation that has to be satisfied as well. Okay. But technically, if we add this green equation at the top to our 3x3 system, all of a sudden we're going to have an over-constrained system. So we're going to have 4 equations and 3 unknowns, right? So you can't have that. You can't have, or at least, in the world of linear algebra, you cannot have more equations than unknowns. Okay. So we have to kick someone out. So we can't have 4 equations here. We have to have just 3. So someone has to get voted off the island. So we're going to eliminate one of the equations in the matrix to make room for our constraint equation. Okay. Because by eliminating one of the equations in the matrix, we're going to have room for our constraint, and then we're back to a happy medium, 3 equations or 3 unknowns. Okay. Of course, the question is, which equation are we going to kick out? Okay. So since this boundary condition is acting on D1, it makes sense to kind of kick out the D1 row of the matrix. So the D1 row is the first row in the matrix. Okay. So we're gonna kick that out that row and replace it with our constraint equation. Okay, so that's kind of the idea. So with constraint equations, constraints, they basically add additional equations for you to solve for in the system. And in order to make room for them, you have to kick out one of your previous equations. Okay? All right, so that's what we're going to do. All right, any questions on this so far? Okay, so let's see how we're going to replace that equation. So kicking someone out is easy, right? So well, depends where you're kicking them out from, but kicking one equation out is easy because they don't really kick and scream, right? But let's see what we replace it with. Okay. Okay. So we're basically going to be taking this equation right here and replacing it into this first row. Okay. So how are we going to do that, right? Because this matrix here is our matrix of 3 equations and 3 unknowns, but our constraint equation there only has D1 appearing into it. Okay. So let's rewrite our constraint equation to be in a bit more of an appropriate form. Okay, so this is going to look strange at first, but trust me, this is going to be what's needed to plug it into our matrix. Okay, so we're going to start our equation as D1 is equal to 0, right? Very simple. So let's make this more complicated. So let's have it be D1 plus 0 times D2 plus 0 times D3 is equal to 0. Okay? And I guess if you want to be really specific, the first term there has a coefficient of 1. Okay? So you have 1 times D1 plus 0 times D2 plus 0 times D3 is equal to 0. Okay? So that equation right there, even though it has a lot more terms, is mathematically equivalent to the one above it, because all the extra terms that I've added just have a 0 in front. Okay. Now, why would I do this? Okay. I did this so that we can kind of extract a vector form from this equation right here. Okay. So what if I extracted the coefficients from the d terms and then put the d terms in their own vector as well? And so if I extracted the 3 coefficients here, it'd be 1, 0, and 0, multiplied by the vector d1, d2, d3, and that's equal to 0. Okay. And so if we factor this out, we put the coefficients into a row vector, we put the variables in a column vector, and so when you multiply these two, it's essentially just the dot product between these two. We get the exact same equation up there. Okay. Okay. So we're doing this so that, if you look at this form right here, and you look at the matrix that we have to plug it into, you can hopefully start to see some similarities, because this vector, this D1, D2, D3 vector, this is exactly the same as what we have in our stiffness matrix system. Okay. And then this row vector right here, this 1, 0, 0, remember, we're kicking out the first equation of the matrix to make room for this one. Okay. Now, if we replace the first row of that matrix with these coefficients, okay, right? So we kick out the old row 1, and so we replace it with this one, right? That's exactly what we need. And so if we kind of put this all together, and so we replace that first row, then we end up with the following system. Okay. We have a matrix set of equations right here, our vector d1, d2, d3. Our right-hand side vector here is little f1, little f2, and we've already applied the mode type boundary condition. So on the bottom side there, instead of little f3, we have our tensile force F, okay? Okay. And so if we replace that first row, the D1 row, with those coefficients, we're gonna have 0 or 1, 0, 0, okay? And then on the right-hand side, instead of little f1, we're gonna replace that with a 0, okay? So this right here is our constraint boundary condition. Okay. So our constraint boundary condition replaced the entire first row of that matrix. Okay. Everything else in the matrix stays the same. So we have a minus Ka, Ka plus Kb, and then a minus Kb. Okay. 0, minus Kb, and Kb. Okay. So all of those K terms, they were kind of left over from the assembly. That's what we talked about on Tuesday. All right. So we're almost done here. So we've gone ahead and we've applied our load type boundary condition and our constraint type boundary condition. There's one more thing that we have to change here, though. Okay. So that little f2, we also need to specify a value for that as well. Okay. Now for node 2, right? Node 2 doesn't have any boundary condition being applied on it at all. So it doesn't have a constraint type boundary condition nor a load type boundary condition. Okay. So what do you do in the case when you have no boundary condition applied? So when you have no boundary condition, you make no modification to the matrix itself. You only have to change the right-hand side value to 0. And so we're going to place that little f2 with 0. Okay. All right. And so with that, we're done. And so we're done applying the boundary conditions. We're done with the assembly. So at this point, you can plug in values for the Ks, you can plug in values for the Fs, and you're going to have a system that you can actually solve. Okay. Now, once you kind of get the system to this point, very rarely will I make you solve these by hand. So this is a pretty simple case. It's a 3x3 system. This one you could probably solve it by hand, no problem. But eventually we're going to reach systems that are, especially once we get to 2D problems, that are, like 12 by 12. And so solving 12 equations and 12 unknowns by hand, I may be cruel, but I'm not unusual. So I wouldn't make you solve it by hand. So after the next example, what I'll show you is how to solve a system like this in MATLAB. Okay. So I know MATLAB, I know MATLAB is not a prerequisite for this class. It's very short and very easy. So you're basically just going to punch the numbers into MATLAB and then solve it from there. Okay. Also, I think a lot of graphing calculators have a linear solver with them as well. And so if you're comfortable using your calculator to solve these problems, then by all means you can do that too. Okay. Okay. Any questions on this process before we do an example? so for the rest of class today, I just have one example to kind of show you the whole process. And so, we've kind of broken up the process into two different lectures here. We started on Tuesday, we completed the constraint type boundary conditions today. So I think it'll be nice to kind of see the entire process from start to finish with just one example. Okay. Okay. So let's look at this example. Okay. So let's consider we have a 3-spring system. So we're gonna have a fixed wall on the left-hand side. So we have one spring that's going to be attached to the wall just like that. Okay. So this spring is going to have a spring constant Ka. We have one node that's attached to the wall. This spring is going to be connected to a wooden block. Okay, so the block is all going to rotate together. So the block itself is actually going to be node number 2. Okay. And the block itself is going to be connected to 2 other springs. And so we have another spring, we'll call it KB, attached up top here. And we're going to have another spring, KC, that's going to be attached on the bottom. Okay. The right-hand side of KB is going to be node number 3, and the right-hand side of spring C is going to be node number 4. Okay. So we have a 4-node system here. And so each of these nodes, they're going to have their respective deformations. And so we have D1 on the left-hand side, D2 for the wooden block, D3, and D4. Okay. All right. And so for this problem, what we want to compute let's compute the values for all 4 of these nodal deformations. So we're going to compute D1, D2, D3, and D4. Okay. Oh, we need some forces here. So let me go ahead and input the forces. So let's say on node 3 here, we have a tensile force. We'll call it F3. Okay. And then on node 4 here, we're going to have a compressive force F4. All right. I have values for all these parameters as well. So we're going to plug in values and find the solution. Okay. Okay. So let me, everyone good with the figure here? I'm going to write down the numbers for the parameters. Okay. All right, so parameter values. So we have our 3 spring constants. We have Ka. Ka is going to be 500 newtons per meter. We have Kb. Kb is 100 newtons per meter. And Kc. Kc is 250 newtons per meter. Okay. And there are 2 Fs. We have F3. F3 has a magnitude of 100 newtons. And F4 have a magnitude of 50 newtons. Okay. Now, these are just the force magnitudes. And so, we have to pay attention to the signs or the directions of our force vectors when we input it in our direct stiffness system. But, those numbers there are just the. Okay. So we're going to solve this problem using the direct stiffness method. So basically following the same process that we did before. Okay. Remember, the direct stiffness method involves 3 separate steps, okay, or 3 steps that you have to do by hand. Okay. Okay. So step 1 is we're going to write out the element stiffness matrices for each element. Okay. So we have three elements here. We have three springs, and so we're going to write out the element stiffness matrix for all three of those springs. Step two in the process is we're going to assemble all of the elements into a single stiffness system. That's step two. Once we have our system assembled, step three is to apply the boundary conditions to said system. Okay. And then step four is to actually solve. Okay. So step four is when you actually plug it into either MATLAB or you plug it into your calculator. Okay. So step one, step two, step three, that's where you're going to spend most of your work. And I guess step four, depending on how quickly you can punch numbers to a calculator, that'll be the last. Okay. So let's start with the first step in the process. So let's start with the element stiffness matrices for each of the elements. Okay. All right. Element stiffness matrices. So when you're writing the element stiffness matrices, you have to kind of take note of two things when you're writing it down. First of all is you have to take note of what type of element that it is. Okay. So that question is kind of irrelevant right now because we've only gone over spring elements. But over the next couple of weeks, we'll be going over different element types as well. So a lot of times the type of the element is pretty obvious from the figure. So just kind of make sure that you kind of take note of that. Okay. But the more important thing for the element stiffness matrix is to make notes of the nodes that it's attached to. Right, and you want to make note of that in the element stiffness matrix. Okay, so let's go ahead and start. So let's look at element A, okay? So element A is a spring. And so our element stiffness matrix for a spring we know is 2 by 2. So we have Ka minus Ka minus Ka, Ka. Element A, we go back up to the figure here, we can see is attached to nodes 1 and 2. Okay, so this is going to be multiplied by D1, D2. Okay, and that's going to be equal to its right-hand side forcing vector F1, F2. Okay, element B. All right, so element B also is a spring. It has a different spring constant, so make sure you kind of plug in the appropriate spring constant here. Okay, so element B has a spring constant KB. So we have KB minus KB minus KB, KB. Okay. Let's look at the nodes that are attached to element B. So we can see element B here is attached to nodes 2 and 3. Okay. So this is going to be multiplied by D2, D3 is equal to F2, F3. Okay. And then we have element C here. Okay. Element C, we have KC minus KC minus KC, KC. All right, once again, we're gonna go up and we're gonna check and see which nodes are attached to element C. And we can see that element C is attached to node 2 on the left, right? So we can see it's attached to the wooden block, which is node 2, and then on the right is attached to node 4. Okay. So this is going to be D2, D4, and F2, F4. Okay. So that's our 3 element stiffness matrices with varying qualities of handwriting. You can see that it's creeping over to the right. So even though they're all the same size, they're all 2 by 2, but yeah, my hand's getting tired. All right, any questions on how we wrote these out? Okay, cool. All right, so the next step after the element stiffness matrix is assembly. So we want to assemble all 3 of these element stiffness matrices into one kind of global system to solve for our 4 unknowns, right? So we know that we have 4 unknowns here, so we need 4 equations. So that means our global system here, or our principal stiffness system is going to be a 4 by 4 system. Okay, so let's go ahead and draw it out. We're gonna have 4 rows, D1, D2, D3, and D4. Okay. And this is equal to the right-hand side forcing vector, F1, F2, F3, F4. Okay. And just so it'll be helpful for us, I'm going to go ahead and draw in the columns as well. Okay, so the first column is the D1 column. Second column is D2. Third column is D3. And fourth column is D4. Okay. Let me move this guy over to the left just to get a bit more room. Okay, so I just moved that left hash over a little bit just so we have a bit more room. Okay. Okay. So this matrix system here represents a system of 4 linear equations and 4 unknowns. And so what we need to do is we need to take our results from the first step. So take all of our element stiffness matrices and insert them or slot them into the right locations here on this matrix. Okay. Okay. So we're going to go one element at a time and make sure that we put them in the right places. Okay. So let's start with element A. Element A here is attached to nodes 1 and 2. So that means the area of this matrix that we're going to block off has to do with nodes 1 and node 2. Okay. And so that means we're going to block off the D1, D2 columns and the D1, D2 row. So that's going to be everything in this section here. So we're going to put everything in element A there. And in fact, you can see that we blocked off a perfect 2 by 2 spot. Okay. So we're going to take our values from element A. So element A we know is Ka minus Ka minus Ka and Ka. Okay. We're going to do Ka minus Ka minus Ka, Ka. Okay. And we're just going to fill in those parts there. Okay. So I'm going to use colors here just to kind of illustrate this, but if you're kind of following along, it's you don't have to use colors. All right, next we have element B. Okay. Element B is connected to nodes 2 and 3. Okay. So let me go ahead and block that area off. Okay. So that's going to be the second and third row intersecting with the second and third column. Okay. So once again, we kind of have a nice kind of 2x2 spot there. Okay. So I'm going to fill in everything from element B into these slots here. So we have a minus KB, positive KB. And where those two intersect, remember, we're just going to simply add them together. We have in this intersection spot, we have KA plus KB. Okay. Okay, so that's two elements down. Let's go ahead and add the third element. Okay, now this one's going to be interesting because, the element C here, the nodes are not, right next to each other in the matrix, right? So element C we know is connected to nodes 2 and 4. Okay. So that means that, we're going to insert this into the second row, fourth row, second column, and fourth column. Okay. Now this is not going to be one contiguous block, and so all the entries for elements here are going to be separated from each other. Okay, and that's fine. And so it's perfectly fine for the entries to be separated from each other. When they're separated, you just have to make sure that which entry goes where. Okay, so let's kind of block those off, right? So we have node 2. Node 2 here is very popular. And so node 2, so second row, second column is going to be this block in green right here. Okay. Kind of on that intersection point. Then we have second row and fourth column. And so that's going to be this spot right here. Okay. Then we have fourth row, second column. So that's going to be this spot right here. Okay. And then we have fourth row, fourth column, which is this one. Okay. So we have our four spots there. So you can still see that we still have our 2x2 matrix. It's just that, they kind of split up a bit. Okay. But we're going to insert the terms that it's still in the right spot. So in the top left here, we're going to add another plus KC. Okay. So that second row, second column spot is going to be pretty full at this point, right? So we have 3 spring constants multiplied by each other. But for all the other parts, we don't have any intersections. So we have a minus KC here, minus KC here, and positive KC in the bottom right. Okay. Okay, good. So we've assembled all of our element stiffness matrices. Now, of course, we have some empty spots here. So everything that's not covered by an element stiffness matrix, remember, you fill that in with a 0. Okay. So you have zeros here, zeros here, zeros here. Okay. Now, the next step in this process is to apply the boundary conditions. But let's kind of take a step back for a second and let's talk about what it means for a 0 to be in the system. Okay. Okay. So whenever you see a 0 in a stiffness system like this, so the 0 there is more than just a filler. It actually tells us some really important information about the system itself. Okay. Notice how each of the zeros is assigned to a particular row and a particular column, right? And so every combination of row and column, you can consider to be kind of a connection between those nodes, okay? So for instance, if we look at the first row and the third column here, okay? Right, so the term there that I kind of circled, pretty heavily right there. That term right there, basically the one way that you can interpret that is that that represents a connection or the relationship between node 1 and node 3, okay? So whenever you see a 0 in the matrix, basically what that tells you is that, those two nodes are not going to interact with each other at all in the physical system. Okay? So that means there's no element connecting those nodes, and there's no way for them to kind of communicate. Okay. And so if we look and see where our zeros are, right? We have quite a few. And so you can see that we have zeros between node 1 and node 3. And so we go back up to our figure, right? And we look and see where nodes 1 and 3 are located. So node 1 is next to the wall right here. Okay. And node 3 is all the way on the right side where the force is being applied. Okay. So there is an indirect connection between them. So node 1 is connected to node 2 through element A, and node 2 is connected to node 3 through element B. Right. So there's an indirect connection between the two, but there's no direct line between node 1 and node 3. So it makes sense that there's a 0 there in the stiffness matrix. Right. Same thing with nodes 3 and 4. So another location where we had a 0 in our matrix was between node 3 and node 4. Okay. So node 3 and node 4, they're indirectly connected with each other. And so node 4 is connected to node 2 by element C, and node 2 is connected to node 3 to element B, but there's no direct line between nodes 3 and 4. Okay. And so it makes sense that there's a 0 in the matrix. Okay. And so this is one thing that you can do to check, because once you kind of assemble the system, right? So you've kind of gone through this step of assembling all the element stiffness matrices. It's always good to do kind of a sanity check to make sure that everything is plugged into the right locations. Okay. Because once you kind of get to this point, and then once you start plugging in numbers, it's hard to kind of go back and fix a mistake. So you always want to make sure with these problems that, you're performing checks kind of throughout the process. So one of the most common mistakes that I see, not necessarily for these types of problems, because a 4x4 system is kind of easy to keep track of. Once we start to get into 2D problems that involve trusses and beams, these matrix systems are going to become, 12 by 12, 14 by 14, 16 by 16. And so, let's say that even for a 12 by 12 system, you have 144 different numbers in this matrix. And so what happens often is that, people are kind of off by one row, or they put a 0 in a place where they shouldn't, and it throws your entire calculations off. And so, you want to kind of save yourself a headache. And so you want to make sure you're doing checks as you're going, so that you catch any mistakes before before it kind of gets too late. Because once you kind of plug it into MATLAB, you plug it into your calculator, and it doesn't turn out right, it's really frustrating. And I will tell you from first experience. So, you want to avoid that as much as possible. Okay. All right. Any questions on this? Okay. All right. So next step here, let's go ahead and apply the boundary conditions. Oops, writing a highlighter here. Okay. So let's go through every single node in the figure, and let's write out what type of boundary condition is there, or even if there's a boundary condition. So it's because it's possible for a node to not have a boundary condition. Okay. Okay. Node 1. All right. So let's go back up to the figure. Node 1, you can see here, is on the left. right? Node 1 is directly attached to a fixed wall. So we know that node 1 is going to have a constraint. Okay. Let's come back down here. Node 1, we know that there's going to be a constraint type boundary condition on there. Okay. All right, node 2. Let's come back up to the system. Okay. Node 2 is our block that's in the middle, right? And so node 2 has a modest springs that are being attached to it, but technically there's no constraint and no force being applied there at all. So node 2, we have no boundary condition. Okay, node 3, let's come back up to the figure here. Okay. Node 3, you can see we do have a boundary condition being applied, and it's a load, right? So we have a force F3 that's pulling node 3 to the right. So we have a force going to the right. Okay. And then finally, we have node 4. Okay. Node 4, we also have a load type boundary condition being applied to on it, but it's a force to the left. Okay. So we have node 4, force to the left. Okay. So we actually, quite a few boundary conditions to apply here. So we have one constraint type boundary condition, two load type boundary conditions, and one no boundary condition. Okay. Okay, so let's start from the top here. So let's start with the constraint type boundary condition on node 1. Okay. So let's kind of remind ourselves what we do when we have a constraint type boundary condition. Okay. So whenever we have a constraint type boundary condition, we're going to replace the row that's associated with that boundary condition. Okay. So for a constraint type boundary condition applied on node 1, we're going to replace the D1 row. Okay. So let's come back up to the system here, and then let's replace that first row in the matrix. Okay, so the first row in the matrix is given by that all those entries there. Okay, so we're going to erase everything that's there already. We leave D1 alone. Okay, because D1 is the unknown. And then we're going to replace it with a set of ones and zeros. Okay, so for D1, we're going to put a 1 in the D1 column. Okay. And then we're going to put zeros in every other entry. So in the D2 entry, we put 0, D3 is a 0, D4 is a 0. And on the right-hand side, we're going to put a 0 there as well. Okay. Okay, so we replaced that entire first row with that constraint. Okay. One thing I should mention here that I forgot to mention earlier. So you notice here that we replaced this entire row with 1 in the diagonal term and then zeros everywhere else. Okay. Now we've only seen examples where the constraint is applied on the first node, right? And so when the constraint is applied on the first node, then you put a 1 in the top left entry, zeros everywhere else. Okay. If you were to have a constraint applied on any other node, so let's say that we have a constraint applied on, let's say we have a constraint applied on node 3. Okay. This is just a hypothetical situation. So we're not actually applying this boundary condition here. Okay. So once again, you're going to erase that entire row and replace things with ones and zeros, but where you put the 1 is not in the first entry. Okay. So actually, if you were to replace this with the proper boundary condition, you would actually put the 1 in the third column. Okay. So the 1 here for your constraint type boundary condition, this always goes in the diagonal entry of that row, right? So whatever entry in that row matches the same, or whatever column in that row matches the same number as that row, that's where you put that 1. Okay. And so it just so happens that the two examples that we did, we had a constraint on the first row, and so that 1 went to the top left corner. But if you're applying constraints on a different node, you want to make sure that you put the 1 in the right spot. Okay. Okay, but of course, for this problem here, we are not applying a fixed support on the third row. Okay, so let me go ahead and bring this back to how it was before. Okay. But just one note, for the future. Okay. So in the future, we're gonna do examples here where where the fixed constraint is on maybe the last row or maybe the second to last row. And so you want to make sure you put the 1 in the right spot. Okay. Any questions on that? Okay, good. All right, so let's go through our other boundary conditions here. So node 2, we can see we have no boundary condition. And so when we have no boundary condition, we're just going to simply replace that F2 with a 0. Okay. Okay. Node 3, we have a mode type boundary condition of F3 pointed to the right. And so let's go ahead and replace that in our matrix here. Okay. Since that F3 is being pushed to the right, we input a positive number there. Just because we typically the positive x-axis goes from left to right, so we put the F3 in there. Okay. And then node number 4 has a low type boundary condition, but it's pushing to the left. So we're going to place little f4 with a minus capital F4. Okay. So we put a minus sign there because that F4 is being pushed to the left, which is in the negative x direction. Okay. All right. So it's a little bit busy, and there's a lot of colors here, but that's essentially our global stiffness matrix. Okay. So the next step in this process here is we're going to plug in numbers. So we're going to plug in values for the Ks and the Fs, and then we're going to plug that into MATLAB and solve for it. Okay. All right. Any questions on how we got to this point here? Okay. Good. Okay. So let's go ahead and plug in numbers. Just because we can. Okay. So we're going to plug in all the values of K, all the values of F. Okay. And so we get the following matrix. So our first row still stays the same. And so the first row is still 1, 0, 0, 0. Okay. That's multiplied by the column vector D1, D2, D3, D4. Okay. And so the first row in the right-hand side forcing vector is 0 as well. Okay. Okay. Second row in the matrix, this is when we start to have our K values. And so we have a minus 500. So I believe that was minus Ka. Next, we have that 2 by that 2 comma 2 slot. So that's Ka plus Kb plus Kc. And so you add all those together, you end up with 850. Okay. Then we have minus Kc, or Kb, excuse me, minus Kb is 100. Okay. So minus 100. And then we have minus Kc, which is a minus 250. Okay. And then on the right-hand side, our middle F2 is equal to 0. So we just plug in a 0. Okay. Okay. Next row in the matrix, and so I'm just going to go a little bit faster just so we can get to the result. Okay. We have a 0, minus 100, positive 100, and 0. Okay. And then last row in the matrix, or excuse me, and then on the right-hand side, we have a positive 100 newtons on the right-hand side force and vector. Okay. And then on the last row, we have minus or 0, minus 250, 0, 250, and then we plug in the force, which is a minus 50. Okay. All right, so that's our matrix system. So now we are ready to solve for this. And so there's only one variable here that we can solve for, very straightforward, which is D1. And so D1 has a value of 0, okay? But for everything else, we're going to need some help. So for the last 10 minutes of class today, I will show you how to plug this into MATLAB and then solve for the results, okay? Okay. All right, so let's go ahead and do that. So let me go ahead and switch to the computer here. And silly me, forgot to open MATLAB, so we're gonna have to stare awkwardly at the screen for a couple minutes. Oh, I hit it right. There we go. Okay. Sorry about that. I probably just opened 2 instances of MATLAB, so now the computer's gonna hate me more. But basically in MATLAB, there's a special kind of operator to solve for linear systems, right? So it's very common, especially for MATLAB users, to solve a system of linear equations. So basically equations of exactly the sort that we have. So we have a matrix of coefficients, we have a right-hand side vector, and so we just want to basically invert the matrix and multiply by that vector to get a solution, okay? Okay, let me go ahead and close. Oops, I didn't want to learn more. Okay, so let me go ahead and close all of these, so that's from optimization. Okay, so to solve a system in MATLAB, you need to define 2 things. So you need to define you need to define the left-hand side matrix of coefficients. And 2, you need to define the right-hand side vector. Okay, so we're going to create variables for both of these things. So we're going to create variables for both the left-hand side matrix and the right-hand side vector, and then fill in the values based on our hand calculations. Okay, so let's start with the left-hand side matrix first. And so, it's just, so we need to define a variable for this. And so it doesn't really matter what you call the variable. But generally, I like to name my variables, something pretty descriptive. So I'm going to name my variable LHS matrix. Okay. And we're going to plug in the coefficients that we just found. Okay. So to build a matrix, actually, let me go ahead and write this out first. To define a matrix in MATLAB, okay, we are going to we're going to define it row by row, starting from the top. Okay. Entries in the same row are separated by, oops, let me go to the next line, by a comma, and use a semicolon to go to the next row, okay? So, there's probably, dozens of different ways to define a matrix in MATLAB. I think for the purposes of our class, I think this is kind of the easiest and most direct method to do that, okay? Okay, let me go ahead and define my variable here, so LHS matrix, okay? And I'm going to define it row by row, starting from the top, okay? So to start a matrix, you need to use square brackets, and so I'm going to make an open and closed square brackets just like that, okay? And I'm going to define the matrix row by row according to those specifications there, okay? So our first row in the matrix from the top is our constraint row, and so that is a 1, 0, 0, 0, okay? And so that's the first 4 entries in our matrix in the first row. And so you can see that I've separated each of those entries with a column. And then to tell MATLAB that I'm done with that row, I'm going to go to the next one. I use this semicolon. Okay. Okay, so now we're going to input the second row. So second row is going to be minus 500, comma 850, comma minus 100, comma minus 250. Okay. So that's the second row in the matrix. Again, I'm using a semicolon to go to the next row. Third row in the matrix is going to be 0, comma minus 100, comma 100, comma 0. Okay. And then fourth row in the matrix is going to be 0, minus 250, 0, positive 250. Okay. Okay, so that is our 4x4 matrix. And so it looks a little strange having it all on one row, but remember, each row here is separated by a semicolon. So we have first row here, semicolon, second row, semicolon, third row, semicolon, and then for the last row, you don't need a semicolon, you just close the bracket there, okay? Okay, and so I'm gonna go ahead and hit enter, and you can see that is our matrix right there, okay? So that's step one. Step one is to define our matrix. Next is to define the vector. So to define a vector, we're going to use a very similar terminology here. Okay, we have a column vector, so everything has to be separated by semicolons, right? And so our right-hand side vector is going to be 0, semicolon 0, semicolon 100, semicolon minus 50. Okay. All right, and so you can see we have our right-hand side vector that's defined now, right? And if you check, make sure, if you look in our notes, this is defined exactly the way that we kind of written it down. Okay, so now that you have the two entries defined, LHS matrix and RHS vector are defined, we can use. So MATLAB has a special operator, a special symbol that says, this matrix and this vector here represents a system of linear equations. And so we can use this symbol to solve for it, okay? And so that symbol is the backslash operator, okay? So if you don't know where the backslash is on your keyboard, it's located right above the enter key, okay? And so it's a slash that kind of starts on the upper left and goes to the bottom right. Okay. And so that's the backslash operator that we're going to use to solve for this system. So the way to use it, to use the backslash operator, okay, all you have to do is you have to put the left-hand side matrix backslash the right-hand side vector. Okay. That's it. So the hard part of using MATLAB is just defining the variables to begin with. So let me do that. So left-hand side matrix, backslash, right-hand side vector, okay? And then you hit enter. And then the result here, that is the solution to your linear system of equations. Okay? And, if you'll notice, it's in the same order in which you defined it originally. Okay, so the first entry here, this 0, that is D1. Okay. Second entry here, that's D2. Third entry here, that's D3. And then fourth entry, that's D4. Okay. So if you go back to the problem, we see that D1 is equal to 0, D2 is equal to 0.1 meters, D2 is equal to 1.1 meters, and D3, or excuse me, D2 is, yeah, D1, D2, D3, D4. I'm sorry. I'm so hungry, I can't count right. So D4 is minus 0.1. Okay. Okay, and so that's all there is to it. And so basically you're defining your matrix, you're defining your vector, and then you're using the backslash operator to compute the solution. Okay. All right, any questions on that? Okay. All right, so that's all we got time for today. And so we'll go ahead and call it here. And so when we come back on Tuesday, we're going to move on to the next step in the direct stiffness process, which is truss elements. And we're going to be working on trusses for quite a while. Okay? So thank you guys, everyone, for coming today. Hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys next week. Yeah. Yeah. Oh.
Whatsoever, and there was so many things over constraints, as well as like M for some MPA.
Okay.
I have the model up right now.
Yeah, let me just look. Let me answer their question. What's feedback real quick? Oh, yeah, yeah. Let me check this out. And then yeah. So the definition of that is I can understand that.
I'm like, I should probably go, and I go and I just regret it. I'm like,
No,
I think so. Yeah. I just think that. The eggs that we need. Here it's kind of hard because it's we didn't so this doing it. Of course. What do you think? The back is oh, yes, right. Yeah. Oh. Okay. So it also looks like this. I'm looking at the actual
So my most quick questions are, canvas, so the middle of the canvas, drawing, and well, thank you for that. Everybody needs to do to make the drawing, okay? So these things I have to show, I can show you that.
Okay, sorry.
No problem. I usually do a lot of this, and I'm sure that